In this video, we're going to look at two questions on the topic of Young's modulus. So first of all, for the first question, it says a steel girder is planted securely between two sides of a round in order to provide a bridge. The total cross-section area of the girder is 30 square centimeters, and the length of the girder is 4 meters. Installed at a temperature of 5 degrees Celsius, the temperature now rises to 20 degrees Celsius. And then the question wants us to calculate the force exerted by the girder due to the change in temperature, assuming the ends do not move. And then it gave us the Young's modulus of steel and also the linear expansivity. So that's basically the fractional expansion due to a change in temperature. Okay, so what I'm seeing right now is that there is a bridge. There's a bridge, and then it gave us the area of the bridge, the length of the bridge, and the Young's modulus, so it's definitely something related to elasticity. And then it gave us the linear expansivity of steel. So my idea is that we can calculate the change in length due to the temperature change from 5 to 20 degrees Celsius, and then from the Young's modulus, calculate the tension within the bridge, which should be the force exerted by the girder due to the change in temperature. And it gave us the ends do not move, so therefore the force and the tension within the bridge should be equal to each other. Okay, so first of all, we have to find the change in length. So in order to do this, we first have to find the fractional expansion. So that is 1.2 times 10 to the negative 7 times the change in temperature, which is 15 degrees Celsius. And then we have to time it by, because this is only the fractional expansion, so we have to time it by the actual length of the bridge. And then this will give us, so that's 60, that is 60 times 1.2 to the power of negative 7, which is equal to, we can give it in 7.2 times 10 to the negative 6 meters. Okay, now we have the change in length of the bridge. What we have to do now is to calculate the force from the Young's modulus. So that is 2 times 10 to 11 is equal to, I'm going to write down the formula first. So that's F over A times L over the extension. This is because it is equal to stress over strain. And so basically the formula for strain is reversed as it is divided by. And so this will be equal to force, let's give it in tension, and then time it by the length. The length of the bridge is 4 over the area, which is 30 times 10 to the minus 4. We give it in cubic meters, and time it by the change in length. And this will give us, then we have to isolate T, so T will be simply equal to 10 to 11 times 30 times 11.2. I'm going to combine the powers of 10, so this will be 10 to the power of minus 10 over the 4. And so therefore T, or force, will be equal to power of 11 times 30 times 7.2, and then time it by 10 to the power of negative 10 over it's 4. So that will be equal to this, and then the units, which is Newton. And this will be the answer to the question, to the first question. Now let's look at the second question. So it says a solid square cross-section mild steel bar of side 2 centimeters is to be bent on the arc of a circle. What is the smallest radius to which it can be bent if the breaking stress of steel is 840 megapascals and Young's modulus is 210 gigapascals, assume that the radius of curvature is much larger than the thickness of the bar. Okay, so what we are looking at right now is that we have a steel bar and then it is bent, and the curvature basically fits in as an arc of a circle, and it gave us breaking stress of steel and Young's modulus. Okay, so let's look at what we can actually get from this. So this is Young's modulus is equal to F over A times L over X. And so basically in this case, okay, so I'm looking over here and seeing that F over A is basically just pressure. So we know pressure, which is this as a breaking stress, and the L, we actually don't know the length of the steel bar, and the X, we don't know L nor X. Okay, so let me draw a diagram to see what exactly is the context. So we have a steel bar with a square cross section, and then basically if you trace its back, it's basically an arc of a circle, and then with radius r. R is what we want to calculate. We want to calculate the smallest value for the r. So let's see, if we want to calculate the smallest value, then basically the steel bar has to be bent as far as possible, or as bent as possible. And so to calculate that, so let's see, from this, the steel bar is definitely in 3-dimensional, so we cannot look at the steel bar as like 1-dimensional line. So there's layers to this bar. So what I'm seeing right now is that at this layer, which is at the middle layer, I would say like the length doesn't change. The length is still L. Now, however, there's 2 layers. So let's say bottom layer. Bottom layer is basically the layer where it's compressed, and then the top layer is basically the layer where it's basically extended or stretched farther apart. So my idea is that we can relate the extension of the top portion of the steel bar to the Young's modulus, and then calculate R. Well, we have to. Okay, so my idea is that we can express the length of the top part of the steel bar in terms of R, utilizing some circular theorems and equations and such. Okay, so first of all, let's start with the circle. Okay, so what we know is that okay, in order to express this is basically a circle, so we have to know the angle. If we don't know the angle, we can't actually do anything from this. So I'm going to assume the angle is to be in radians. So L is equal to theta r. And okay, so right now this equation is just the expression of the length L, the initial length of the steel bar in terms of the angle and R. And let's see, so at the top part is basically L plus some kind of change in L, right? A change in L. And then this is equal to theta times R plus, and then assume the radius curvature is much larger than the thickness of the bar. So we might use this information later in the question, but I'm not sure right now. So the thickness of the bar is basically 2 centimeters. However, it's from the center, measured from the center, so it's half of it, so that's 0.01 in meters. Okay, so now what I'm saying right now is that we don't know anything about theta, we don't know anything about length. So my idea is that simply let's express this in terms of L first, because we can actually rule out two variables in this case. Okay. So what I'm seeing right now is that these two, they are recurring. So we can express this. So we put L in, so L plus delta L is equal to L plus 0.01 times theta. So what we know simply is that 0.01 theta is equal to the difference in L. Okay, we got something new. Now we have to relate this back to Young's modulus. So let's see, we know the pressure, so what we want simply is the strain. How do you calculate the strain? Now from this, we actually expressed the change in length from this. Okay, so now we can actually calculate the strain. So let's see, strain will be equal to the change in length, so 0.01 theta over L. Now there's two variables, so actually we can link this back. So my idea is that we can basically just express L back as theta r. So theta r, and then this basically gives us 0.01 over r. Okay, so we got the strain in terms of r, which is excellent. So we basically have an entire equation with only r as the variable. Okay, so now we link this back to Young's modulus. So the Young's modulus 210, I think. Yes, and then it's gigapascals, so that's 10 to the power of 9 is equal to the pressure that is 10 to the power, it's mega, so it's 6, and then times by the strain. However, it's a reciprocal of the strain, which is r over 0.01. Okay, and then now we can simply calculate r. So this is 210 times 10 to the power of 9 times 0.01 over 840 times 10 to the power of 6. And it gives us 2.5 meters. And this is essentially the answer to the question.